All right. 15.2 part 2. And I realize I look back at the notes. Today's not really a marathon. It's more like a 10K or so.
Homework for marathon. I prefer
More like a triathlon, like sections down in the homework.
the Ironman.
So we're going to talk about line integrals on vector fields and the differential form of line integrals. Yeah, even the title is long. This. All right, so we're going to start out. I'm going to start out by asking you a couple of questions, and then we'll get into our lecture. So, say we have a problem, and we have a surface. Z equals f of x, y, and the problem says find the lateral area above the curve C. So you have some function, some surface Z equals f of x, y, and the problem says find the lateral area of the surface above the curve C, and C is in the xy plane. What is this problem asking us to do? So first off, what is lateral? When we're talking about the lateral area, what are we talking about? What does lateral mean? Lateral means the side. So we want that area, the side of this surface. So how do we find the area of the side of something? So let me draw a quick picture. So here's our picture. We have some curve in the xy plane. So that's C. And we have some surface above the xy plane. That's Z equals f of xy. So the lateral area of the surface above the curve C in the xy plane. So I'm going to connect. So I'm just drawing some projections. So there's a projection up onto the surface. So we're talking about this lateral surface area, this piece. So Lee says we're talking about the line integral along C of f of xy ds. So this is asking us to do the line integral. So we're thinking of this function as a height. So this is our height above the xy plane, and we're at each point on the curve we're multiplying that little length of ds by the height at that portion. So that's going to give us a little area. The ds is our width, and the f of xy is the height, and we're adding up all those little areas. So this is a line integral problem. So in your homework tonight, there's a set of problems that says find the area of the lateral surface, and it gives you some information. It gives you a function. It gives you a curve. What it's asking you to do is evaluate this line integral. So lateral surface area. One way we can interpret this line integral of a scalar function, is a lateral surface area. I talked about it the other day. I said the area of the fence. So this the area of the fence. This and this function gives us the height of the fence, and this is our where we're putting our fence posts. The curve is where we're putting our fence posts. All right. So my other question is, we have a wire. We have the wire in the shape of the curve C. And its density per length, mass per length, is some function of x and y. So the density varies with position. And the problem asks you to find the mass. So what is this problem asking us to do? This is a line integral problem. Our mass is going to be the line integral over c, f of xy, ds. So this is another line integral problem. So the couple of the kinds of application problems that you'll be asked in the homework. It'll ask you to find the mass of the wire, bent in some shape. Yes.
Is f of x, y a vector field?
No, this is just a scalar, a density. So it would be like grams per inch.
Do we have to change it to one or in the parametric way?
Yeah. So you'd have to. So we go through the same procedure that we did the other day. You'd have to parameterize the curve and evaluate the line integral that way, and then express your function in terms of your parameter and do the line integral that way. Okay. Same thing here. We would parameterize whatever curve we had and express f of xy in terms of our parameter. All right. So I just wanted to make sure we were all on the same page with those kinds of application problems. All right. So let's talk about line integrals and vector fields. So what we want to do now, we're going to start with what we talked right at the end of first semester about work, and we said that work done by a force was the force vector, and we take the dot product with the displacement vector, and we said that the force only does work in the direction of motion. So that's why we ended up doing the dot product. So what we're going to do now is we're going to talk about line integrals with vector fields motivated by this idea of work. So we're going to look at the idea of work to come up with a way of thinking about line integrals and vector fields. So what we want to do is find the work done by a force. So our force vector is some function of x, y, z. So our force is a vector field. So at every point in space we have a force vector. And we're moving a particle along some curve. And we're going to say we're on a smooth curve. So our particle is moving on some kind of curve in space, and we want to find the work done by this force as the particle moves along this smooth curve. So our argument's going to be, at this point, this should be a very, very familiar argument. So here is our picture in space, our axes. I think by this point you guys could probably construct this argument. So here's our curve, and we're going to look at this curve from point 0 to some point n. And we're going to divide the curve into small pieces. So I'm going to just pick this piece here. So we're dividing our curve into little intervals. And at this little interval we have a force vector. So I'll draw that in red. So here's F at that little position. And the length of this little interval is delta S sub I. So we're dividing our curve into little pieces. And we're going to sum the work done in moving the particle along. We're going to find the work done moving the particle along this one small piece, and then sum that over the portion of the curve that we're interested in. So let me draw a magnified version of this little piece. So we're going to magnify. So here's delta S sub I now. Here's our force vector at this point in delta S sub I. Draw that in. So there's F. And I'm going to also draw in a tangent vector. And I'm going to call this F sub I, because that's the force vector at this ith subinterval. And the blue vector here is our tangent vector at that particular point. So the force, only the component of the force in the direction of t sub I does any work on that interval. The force only does work in the direction of motion. So we're going to say that F sub I only does work in the direction of t sub I. So our small increment of work in that little ith subinterval is going to be F sub I dot t sub I times delta S sub I. Delta S sub I is how far we've moved in that direction, and t sub I is the direction that we're moving. So our small increment of work delta W sub I is F sub I dot T sub I times delta S sub I. And we're going to sum this over the length of the curve that we're interested in, take the limit as delta S sub I approaches 0, and we come up with our definition of a line integral on this vector field. We're taking the sum, and summing as the limit goes to, delta S sub I goes to 0. So we're going to say that the work done by this force moving the particle along this curve is going to be the integral, the line integral on C of F dot T ds. So there's how we're going to evaluate this line integral with this vector field, or this is how we're going to express it. Yeah.
So how do you denote if it's a line integral, like, rather than just saying it?
That's what the C tells us, that we're integral over some curve. And then later on we get to learn some other fancy symbols where we'll do something like this. And that will tell us we're on a closed curve. And we'll do the same thing with surface integrals and volume integrals. We'll get to put these little circles in there. And we'll get to that, is that in the next section? I think so. So we'll get to learn some new symbols. So this is how we're going to express our work. So this is our line integral of this vector field. We don't want to have to calculate the unit tangent vector, and we don't want to have to work with ds. We don't want to have to parameterize our curve in terms of the arc length. So we're going to say that we're going to remember, or my favorite word, recall, that our tangent vector is r prime over the length of r prime. And if we parameterize our curve, that ds is the length of r prime times dt. We talked about this. This is how we evaluated our line integral with our scalar field the other day. So ds is the length of r prime dot dt. So we can say, rewrite our line integral. So the work is the line integral of c f dot r prime dt. And we write this as f dot dr. So f dot r prime dt is f dot dr. And this is our definition of our line integral. So motivated by what we did with work, we're going to define the line integral of any vector field on a curve. So we don't just have to be talking about force and work and distance, that kind of thing. So this is our definition of a line integral of a vector field. The integral of f dot dr, and this is f dot t ds, and we're going to evaluate this as the integral from a to b of f expressed in terms of our parameters. So we're expressing f in terms of our parameters. So if we parameterize our curve, f dot r prime of t dt, where our curve is given by, so we're parameterizing our curve, r of t. For a less than or equal to t, less than or equal to b. So this is how we're going to define our line integral of a vector field. F dot r prime dt for our parameterized curve. Does that make sense? And using that argument, it's the same kind of argument we used it in chapter 14 for pretty much every integral we did. So we're doing the same thing here. All right, so let's evaluate some of these line integrals with vector fields. And so where we're going with this, what we're doing is we come up with this idea of a line integral of a vector field. In the first section, we talked about the divergence and the curl and conservative fields. Well, it turns out that conservative fields have really nice properties when you do line integrals. So if you have a conservative field and you do a line integral on this conservative field, some nice things happen to simplify your work. If we do the line integral of the cross of the curl, interesting things happen. If we do the line integral of the divergence, interesting things happen. So that's kind of where we're going. And then we'll go into, we'll move off away from line integrals, and we'll talk about integrals over surfaces, of vector fields over surfaces. And then we'll talk about do triple integrals and talk about vector fields and volumes. So that's where we're taking all of this stuff. All right, so let's evaluate this. So we want to evaluate the line integral on our curve f dot dr. Where f, our vector field, is xyi plus yj, and our curve is given by r of t, which is 4 cosine ti plus 4 sine t j hat for 0 less than or equal to t less than or equal to pi over 2. So before we start doing any work, what is this curve? What is this circle? And because we're going from 0 to pi over 2, it's a quarter circle. It's a quarter circle, so we're looking at this, we could think of this as the work done moving a particle around this quarter circle by a force that varies this way. So first we're going to need to express our f, our vector field, in terms of our parameters. So f is, how are we going to write f? 16 cosine t sine t. X equals 4 cosine t, y equals 4 sine t. Plus, whoops, I forgot, I haven't need my I hat plus, and y is 4 sine t, so we just have 4 sine t j hat. And we're taking the dot product, dr is r prime dt, so we need r prime. So r prime here is going to be minus 4 sine t I plus 4 cosine t j. And we're going to take the dot product, so f dot r prime. So what's f dot r prime going to be here? Minus 64 cosine t sine squared t plus cosine t sine t. And we're going to integrate this over our curve. So we parameterized our curve was parameterized. We expressed our f, our vector field, in terms of the parameters, and we took found the dot product. So now we're going to integrate our line integrals from 0 to pi over 2 of this quantity, minus 64 cosine t sine squared t plus 16 cosine t sine t dt.
The difference between this and what we were doing the other day was that the other day we only had c, we didn't have...
And our f was a scalar, not a vector.
Oh, okay.
F was a scalar function. So our integral, it's set up nicely, so all of our integrals we can do with a u substitution. And when we evaluate this, so we get minus 64 thirds sine cubed t plus 8 sine squared t. And when we evaluate that, we end up getting minus 40 thirds. So questions on setting that up?
So what is the negative?
Negative would have to do with the direction. If we thought of that as a force, the force would be doing negative work.
It's an opposite direction.
Opposite direction, yeah, if that's how we want to think of it.
Direction.
Right. Right. And our forces, our y or our x component of the force, if we think of this as a force, is in that interval is positive, right? And it's moving backwards, right? So if we want to give it a physical interpretation, yeah. Lane.
So, does this kind of assume that all forces are conservative? Because, for example, if you did it around a whole circle, it would be 0. What would happen if the force dealing like gravity? But
Right.
If the object, if the force had given the object a bunch of energy,
Right. So it doesn't. We're not assuming that the forces are conservative. It might turn out that this force is conservative. But if we evaluate on a closed, and we'll get to that later. If we evaluate on a closed circle for a non-conservative force, we would get something that wouldn't be 0.
Okay.
Okay. All right. So let's look at another example, and then we will talk about the differential form of line integrals. So we'll have to do a little more work for this example. No pun intended. So find the work done. RDR, right. Done by F is YZ I hat plus XCJ plus XYK. Make sure yes, that's what I want my force to be. And we're moving a particle from 0, 0, 0 to 5, 3, 2. All right, so what do we need to do here? We need some kind of parametric equation for our curve. Well, what kind of curve is this? It's a line. So we need a parametric equation for this line. So do we remember what parametric equations for lines look like? And I'm going to write a general equation. So it'd be x1. It's x1 plus at. I hat, that's our x component, plus y1 plus bt. It's j hat plus z1 plus ct k hat, where a, b, and c are our direction numbers. And x1, y1, and z1 are a point on the line. So what's going to be the easy point to pick on our line that will simplify our work? Pick that 0, 0, 0. What are our direction numbers going to be? 5, 3, and 2. The direction numbers are just the components of a vector that points in the direction of the line. So the vector 5, 3, 2 is going to point in the direction of this line. So we can say that r of t, our parametric equation of this line, is just going to be 5ti plus 3tj plus 2tk. And what's our parameters is going to vary from what to what? 0 less than or equal to t less than or equal to 1. And that will take us from 0, 0, 0 to 5, 3, 2. All right, so there's our parametric equation for our curve. Now we need to express f in terms of our parameter. So f of t is going to be what in terms of our parameters, or I guess parameter? 6t squared I hat plus 10t squared j hat plus, what is it, 15t squared k hat. So there's our force expressed in terms of our parameter. Now we need our prime. Just going through step by step, everything we need. Our prime is just going to be a nice easy vector, 5i plus 3j plus 2k. F dot r prime is multiplying our components, so we get 30t squared plus 30t squared plus 30t squared. Wonder how that happened. 90t squared. So our line integral, so we're finding our work is going to be the integral from 0 to 1 of 90t squared dt, which comes out to be 30. So it'd be 30 units of work done moving that particle by that force. So questions on that? So setting up line integrals with vector fields, just a few more steps than we used before. Parameterize our curve, express our vector in terms of the parameters, find our prime, take the dot product, and then integrate over the limits of our parameters. All right, are we good? We're halfway done. We've got 5K. We're through 5K.
So that would have been like the one class.
That would have been one class.
That would have been all we did today.
That would have been all you've done. All you did.
Yeah, but we still have class. Mr. Beaver?
Yes.
We don't have, we don't have, you have the final exam part 2 on like the Thursday before we graduate. Do we even come to class that day? I don't think we have a class.
Our last day is Tuesday and Wednesday.
So I think we have senior checkout on Thursday.
Yeah, no, it's
I think we don't.
I think our last day is Wednesday.
Okay, let me.
And I think the block days are Tuesday, Wednesday.
No.
So, yeah, next week, the week after next week, we have 3
All right.
That's it.
So let's look at the differential form of line integrals. We've talked about a couple of different forms for line integrals, and what we want to do now is find some kind of connection, how the two are related, how we can express them, how we can think about them being connected. So, just a quick summary of what we've done so far. We have a curve, C, and we have the line integral of a scalar field, f of x, y, ds, and we evaluated that. This is what we did the other day. The integral from a to b of f of t So we express our function in terms of the parameter, and then I'll put this as f of r of t. So we express our function in terms of the parameter times the magnitude of r prime of t dt. So this is how we evaluated a line integral of a scalar field. We expressed our function in terms of our parameter on the magnitude of r prime dt. And for a vector field that we just did, that we just talked about, we said that f is our vector field. The integral over our curve of f dot dr. The other way we could express that, other couple of ways, f dot t ds, if we're talking about our curve parameterized in terms of the arc length, and that was the same as we could evaluate that as the integral from a to b, and we express our vector field in terms of our parameter, and we take the dot product with r prime dt. So we want to find some way that we can relate these two things. How is a line integral of a vector field related to this idea of a line integral of a scalar function? So to make this connection, we're going to write f, our vector field, and for now I'm going to be talking in the plane. We're going to write this with the notation m I hat plus n j hat, where m and n are some functions of x and y. So we've talked about this before. And our curve, we're going to say c is some position vector. So we parameterized our curve, and that's x of ti plus y of tj. So that's our parameterized curve. Well, now if we form f dot r prime, we form this dot product, we get m dx dt plus n times dy dt. So r prime is just x prime I plus y prime j, make that dot product. And the integral, our line integral, line integral of f dot dr is going to be the line integral over c of m dx dt plus n dy dt dt, and this is just equal to m dx plus n dy. And with three variables, same idea with three variables. If f is a function of x, y, and z, so this is going to be mi plus nj plus pk. Then our line integral turns into integral along our curve of m dx plus n dy plus p dz. I'll put these in parentheses. to remind us that we're integrating that whole thing. So our line integral of our vector field turns into the sum of these scalar line integrals. So that's our connection between those two. We can think of this line integral of a vector field as the sum of these scalar line integrals. And often we'll see we'll use f expressed this way, and our line integrals will be easier to evaluate if we think of them in this form. And we call this form the differential form of a line integral. So this is our differential form of our line integral. So we have a scalar line integral, we have a vector line integral, and now we have our line integral in differential form. So a couple of important things to remember about line integrals. So we have three ways that we can think of them: scalar field, vector line integral, and differential form. So I'm going to make a note here for the. And we have the differential form for a line integral. The value of a line integral is independent of the parameterization of C. So we can parameterize C any way we want. The value of the line integral is going to be independent of the parameterization. The orientation of our curve. So depending on how we parameterize our curve, we talked about that the other day, we parameterize it differently. The parameterization introduces an orientation. We're saying this is the positive direction. Yeah.
So what do you mean by independent?
Well, we could, so if we parameterize the line, the example we did with the line last time, if we chose some other equation for the line, so we chose a different point on the line, a different expression for the vector. So if we parameterize that line differently, we would evaluate our line integral. We would come up with the same answer because everything adjusts with that parameterization. So we parameterize a circle with, instead of 4 sine ti plus 4 cosine ti plus 4 sine tj, we switch those two around. We still get a circle. It's a different parameterization, but when we evaluate our line integral, we would get the same result. Okay? The orientation of our curve affects the sign of the vector line integral. So it affects the vector line integral and our differential form, because we came up with the differential form from the vector form. So changing the orientation is going to change the sign. If we think of changing the sign, then our unit tangent vector points in the opposite direction. So we're taking the dot product in the opposite direction. It does not, the orientation of the curve does not change the value of the line integral for a scalar function. And if we interpret our line integral of our scalar function as an area, traveling along that curve in a different direction is not going to change the area of that fence. I'm going to change the area of that lateral surface. So going in one direction or the other doesn't change the area. So changing the orientation reverses the signs of these line integrals. Doesn't change the value of our scalar line integral. All right, so let's look at a couple of examples using these ideas, and then we'll be done for today. So we want to evaluate our line integral of 2x minus y dx plus x plus 3y dy. And where our curve is an arc on y equals x to the 3/2 from 0, 0 to 4, 8. So here we have a differential form. We have our line integral in differential form. So m is the function in front of dx, so m is 2x minus y, and n is x plus 3y. Now in order to evaluate this line integral, we need everything in terms of one parameter. So what's going to be an easy parameter to use here? Anybody have an idea? So our curve, the curve that we're looking at is expressed in terms of y as a function of x. So let's let x be the parameter. We could say x equals t, but I'm just going to say let's let x equal the parameter. So the parameter is x. So dy we could separate into two integrals, but here we have, so we'd have to switch the x, so we'd have to express x in terms of y, and here we'd have to express y in terms of x. Does that make sense? A multiple integral. Right, x is in a constant. Okay. So dy, just going to take the derivative here. Dy is 3/2 x to the 1/2 dx, and x varies from 0 to 4. So now I can just substitute all of this stuff into my integral. So we have the integral from 0 to 4. Our parameter varies from 0 to 4. X varies from 0 to 4. Of 2x minus y is x to the 3/2. Dx is just dx. Plus x plus 3 times x to the 3/2, and dy is 3/2 x to the 1/2 dx. So now we have our entire integral expressed in terms of x, in terms of our parameter. And we just have nice exponents that we have to evaluate. If I combine this all into one, I get 9/2 x squared plus 1/2 x to the 3/2 plus 2x dx, and we evaluate that to 592 bits. So that's an example of how we would evaluate a line integral in differential form. All right, I want to do one more example, and then we'll be done. So we want to find the integral along C of f dot dr on our two paths. And we want to explain the results. F, our vector field, is given by x squared y I hat plus x y to the 3/2 j hat. And our 1 is t plus 1 I plus t squared j for 0 less than or equal to t less than or equal to 2. And let's do this in differential form. So we're going to evaluate these line integrals in differential form. Just to practice doing that. So yeah, essentially. F dot. What's that? R2. I'll give us R2 after we evaluate this one. All right. So M for this one, for our differential form, what is M? X squared y and x y to the 3/2. X for our parameterized function, what is x? T plus 1. So dx is what? 1 dt. dx is dt. Y is t squared. So dy is 2t dt. So whenever we're doing line integrals, we want to express everything in terms of our parameter. So whatever our parameter is, here our parameter is t, so we're going to express everything in terms of our parameter. So our line integral of f dot dr is the integral from our parameter varies from 0 to 2. M in terms of our parameter, t plus 1 squared times y is t squared, and we're multiplying that by dt, plus n in terms of our parameter is t plus 1 times y to the 3/2 times dy. Why did I put 2 dt here? 2 dt dt. So there's our line integral. That's the integral that we need to evaluate. I can multiply this out. These not going to be a difficult integral to evaluate. I can square this, multiply it out. I just end up with powers of t. So I'm not going to go through the evaluation, but we end up with a value of 256 this. So wrote our line integral in differential form, expressed everything in terms of our parameter, and evaluated our line integral. So we want the same field, we want this same f, but we want a new path. So let me see if I can remember how to do this. This. Copy, okay. And then I'm going to go here, and I'm going to paste. And then I'm going to do this. Oops. All right, I think I almost had it. Okay, so we do that, and then I do this, and then I move it up here. There we go. All right. So there's my field. I just didn't want to rewrite that. It probably would have been faster if I did rewrite it. But I want to remember how to do that. All right. So there's our field, and now our path R2. We want to evaluate this on our second path. R2 is 1 plus 2 cosine t I plus 4 cosine squared t j for 0 less than or equal to t less than or equal to pi halves. So let's express x and y, express everything in terms of our parameter. So here x equals 1 plus 2 cosine t. So dx is going to be minus 2 sine t dt. Y is 4 cosine squared t. So dy is minus 8 cosine t sine t dt. And now we can write our line integral. So the line integral of m dx plus n dy, in this case, is the integral from 0 to pi over 2 of x squared y. So I get 1 plus 2 cosine t squared times 4 cosine squared t times minus 2 sine t dt. I'm going to put this in brackets because I'm going to go to a different line here. Plus, now we need our second part, n, and I get x, y to the 3 halves, 1 plus 2 cosine t times 8 cosine to the 3rd t times r dt, r dy, sorry, minus 8 cosine t sine t dt. That's a long integrand. We can simplify this. I'm not going to go through the process of evaluating this. I'm going to give you the results. So the problem's not, this problem, particular problem, is more about setting, one, practice setting these up in differential form, and two, we want to interpret these results. So when I evaluate this, I get minus 256 over 5. So we want to interpret that. Why would that happen? We went the opposite direction. So let's take a look at for R2. R2 at our parameter equals 0. If I plug in 0 into R2, I get the point 3, 4. If I plug in R2 of pi over 2, I end up with the point 1, 0. If we go back to R1 of 0, and if we go back, we said R1 went from 0 to 2, and this was R1. So I'm plugging 0, 0, and 2 into R1 here. R1 of 0 is 1, 0, and R1 of 2 is 3, 4. So Sean was right. Our path took us from one point to the other points in the opposite directions. So basically we parameterize this curve in two different ways with opposite orientation. Yeah.
So the differential form would make it easier to solve? Or
Not necessarily. Just a different way, and we'll use a differential form for other things in the future. So we'll have a special theorem about this, a particular type of line integral in differential form. And it turns out it's a really cool, really nice thing, and it shows up in physics a lot. So we need to know about the differential form because we're going to apply it here. Especially on this one, this is a lot of work.
Yeah.
And on this first one, I think it would be easier to find f dot r prime than to go through this. But what we're doing is practicing getting familiar with this form so that then we can use it for something else in the next couple sections. All right, questions on differential form? All right. You know just about everything you need to know about line integrals now. Now we can start talking about line integrals with conservative fields and with special circumstances and start doing really cool things with line integrals. Or I guess even cooler things with line integrals. So we're already doing cool things with line integrals. All right. All right. I have not. We should check homework.